A polished steel component looks completely solid, but dive down to the atomic level and you find a chaotic labyrinth of vibrating, interacting structures. To engineer parts from these materials, we must translate that physical chaos into predictable, large-scale behavior. We do this by quantifying the material's macro texture and micro texture. This diagram outlines the analytical framework. Left, a polycrystalline cube shows how atomic clusters lock into individual grain structures. To quantify them, engineers rely on 5 mathematical representations in the center column. These map onto 4 distinct projection spaces, yielding workable geometric models. These dashboards appear complex, but they are built on a highly constrained mathematical logic. Before you can predict how a finished component will bend, shear, or break, you must build that entire mathematical framework from the ground up, starting with a single point in an empty coordinate space. We start with a completely abstract, empty 3D space. Within that space, we define a single point of origin using a position vector, r. By applying non-coplanar basis vectors, labeled a, b, and c, along with simple integer multipliers, we project that single point outward to generate a mathematically perfect periodic array. This resulting infinite 3D grid is the crystal lattice. It acts as the purely spatial skeleton of the material. But a coordinate skeleton isn't physical matter. For that, we need the motif, the actual physical atom or cluster of atoms that will occupy the structure. This diagram visualizes the core equation of crystallography. We take the purely mathematical crystal lattice, the blue wireframe, and we combine it with the physical motif. The sum of those 2 variables defines the complete physical crystal structure. Every piece of solid crystalline matter on Earth, from a grain of salt to a jet engine turbine blade, is built through this exact modular equation. The outer shape of that resulting crystal depends entirely on its boundary limits. By manipulating 3 axis conditions and 3 angle conditions, we generate distinct foundational geometries. This table breaks down the 7 fundamental crystal systems dictated by those conditions. If you look at the bottom 2 rows, you'll see the hexagonal and cubic systems. These 2 specific structural forms dominate the standard industrial metals we use every day. However, establishing the outer shape is only the first step. Atoms do not only bind to the absolute external corners of these geometric shapes. This graphic details the 4 spatial centerings allowed inside those shapes. An atom can sit exclusively on the corners in a primitive configuration, or it can take up a body-centered, face-centered, or base-centered position, altering the internal geometry. In 1848, the physicist Auguste Bravais mapped out exactly how these external systems and internal centerings could combine to seamlessly fill a 3D volume with repeating translational symmetry. His proof showed that while multiplying the 7 systems by the centerings seems to yield 42 apparent mathematical combinations, physical symmetry overlaps cancel most of them out. The definitive universe of valid space-filling lattices is limited to exactly 14. Despite the near-infinite variety of materials in the known universe, their physical foundation is constrained to just these 14 distinct structural blueprints. But those 14 Bravais lattices only dictate translational symmetry, how a shape repeats in a straight line through space. We must also account for point group symmetry. These are the specific operations an object can undergo around a fixed central origin point, like a rotation, a reflection, or an inversion, while remaining structurally identical. This schematic maps the absolute limit of structural possibility. It combines the 32 independent point groups on the left with the translational symmetry on the right. This calculation yields exactly 230 space groups. These 230 groups provide the complete description of 3D crystal symmetry. This mathematical boundary serves as the primary governor for macroscopic physical, mechanical, and electrical material properties. While nature operates within those 230 distinct space groups, materials engineers attempting to study them face an observational roadblock. We rarely get to interact with that full, pure mathematical spectrum. To observe what atoms are actually doing inside a dense solid, we have to bombard the material with energy. We primarily rely on X-ray diffraction, or XRD, which measures how energy waves scatter off the internal lattice. The problem is that this observation method introduces a disruptive physical limitation known as Friedel's law. This maps Friedel's law. On the right, the law dictates X-ray intensity scattered at one plane perfectly matches the intensity off its opposite plane. Look left. The material is genuinely asymmetrical. Because XRD outputs identical intensities, it creates the centrosymmetric illusion. The machine is blinded. It is an uncomfortable reality of the discipline. Our primary measurement tool artificially forces the universe to appear perfectly symmetrical. It creates a gap between true physical reality and the limits of observational data. That illusion acts as a filter on our mathematical models. The 32 true point groups cannot all be accurately mapped if we cannot detect their asymmetry. This flowchart visualizes the resulting data bottleneck. The machine forces the 32 crystal classes through the filter of Friedel's law, collapsing them down to what can be uniquely observed. What survive are the 11 Laue groups, shown as distinct geometric projections. Because of this hardware limitation, attempting to evaluate a bulk material against the full universe of the 230 space groups is unnecessary for macroscopic texture analysis. Instead, engineers adapt. They utilize these 11 observable Laue groups as their active operating system, using them to define the practical orientation space boundaries required to calculate structural integrity. Theoretical physicists will continue to map the 230 structural realities of the atom, but the engineers building the physical architecture of the modern world rely on the 11 specific frameworks allowed by the limits of human observation.